Hello everyone, welcome to the sixth video. Today we'll be doing conservation of energy, and this is example 14-87 from Russell Hubler 14th edition, and why conservation of energy versus the work and energy. So if you have conservative forces, you could do conservation of energy, and conservative forces as in gravity or spring. And if you have, let's say, force of friction, which we had in the last example, we can't use conservation of energy because work due to friction is not conserved, right? So here the question is, the block has a mass of 20 kilograms and is released from rest when S equals 0.5 meters. If the mass of the bumpers A and B can be neglected, determine the maximum deformation of each spring due to the collision. Alright, so here we can see that we have springs and gravitational force. There's no friction or anything, so we know that we can use conservation of energy. So the formula for conservation of energy is T1 plus V1 is equal to T2 plus V2. So in this case, we're starting from rest, so we know T1 is going to be 0, and we're going to end at rest as well, right? So our T2 is also going to be 0. Because when we have the maximum collision, the velocity is going to be 0. So now we need to figure out what our V1 and V2 are, and that depends on what we choose as our datum, right? So let me just draw quickly what we kind of have here. So this is our initial state, right? And our final state, we're going to have something like this here. So we know that this distance here is 0.5 meters S, and then this is going to compress the top spring and the bottom spring. So I'm going to choose this to be the datum. And if I choose that to be my datum, I know that initially my V1 is going to be 0. And then if this compresses in my final position, I'm going to have the 0.5 meters from S. I'm going to have the compression of the top spring, and I'm going to have the compression of the bottom spring. So let's call that SA and SB. So now that we have our datum specified, I'm going to write final here. All right, we can solve for our V2. And V2, we're going to have V2 due to gravity, and we're going to have a V2 due to the elastic energy, right? So our V2 due to gravity is just going to be the mass times the gravitational acceleration, and we're going to multiply by that by our total compression distance, right? Which is going to be minus SA minus SB minus 0.5. And why am I writing negatives here? It's because that we're losing energy, right? We're losing gravitational energy. We're going from a higher position to a lower potential energy. So that's why it's a negative here. And my elastic energy is going to be just half kx squared, right? And so here it's going to be half time my Ka, which is 500, and then Sa squared, which is our compression, plus half times Kb, which is 800, times Sb squared. Awesome. So now we have our V2, but the thing here is we have basically one equation here, one equation with two unknowns, SA and SB. SA and SB. So we need to relate them somehow with another equation so we can solve. So what other equation can we use? We can relate we can use kinetics in here, right? We know our force, so we could use kinetics here, right? So in our final state, when we have our compression over here, I know that my force due to the spring is going to be here equal and opposite because it's our maximum collision rate, and this is Fs. So I know that Fs is equal to Kx is going to be the same for the top spring and the bottom spring. So I'm going to have 500 times Fa is equal to 800 times Sb. And solving for Sa, it's going to give me 1.6 Sb. Perfect. So now I have basically two equations, equation 1 over here and equation 2, and two unknowns, Sa and Sb. So now I can solve. So plugging it into my conservation of energy, I have 0 equals 20 times 9.81 minus Sa minus Sb minus 0.5. I'm going to plug in my 1.6 Sb 0.5 plus half times 500 is 250 Sa square plus 400 Sb square, and I'm going to take out the negative here, so I'm just going to have minus 196.2 and I'm going to plug in my Sa and Sb. 1.6 Sb plus Sb plus 0.5, and plugging in Sa is equal to 1.6 Sb here, I have plus 640 Sb square plus 400 Sb square. Simplifying even more, this is negative 196.2 times 2.6 Sb is going to give me negative 510.12 Sb, and negative 196.2 times 0.5 is negative 98.1, and again plus 640 Sb square plus 400 Sb square. So we have basically a quadratic equation, right? So I'm going to rewrite that as 1040 Sb square minus 510.12 Sb minus 98.1. And we know our quadratic equation is Sb equals negative b plus minus square root of b squared minus 4ac divided by 2a. Just the plus is going to give me 0.638 meters. And solving for Sa, we get Sa is equal to 1.6 times 0.638, which is 1.02 meters. Alright, and that's our answer.